So welcome back to System Software. We're going to review the functions with parameters using the examples from the CodeGen 2 project. There are two IR files given to you. So one function is called main. The other function is called param_test. Main has several local variables, including 8 that we're going to use as parameters to the param_test function. We assign each of these parameters to a different number, 1 through 8, and then we call param_test passing these 8 parameters and saving the return value in X. Questions on what this simple IR function program does? Yeah.
Okay, so basically the colon equals like the definition.
Assignment, yeah.
Yeah.
Yeah, that's right. All right, so param_test is what main is calling, and it defines its own set of local variables, even though some of them have the same name as main. They're local variables to this function, so they're not the same variables. There are 8 parameters specified here as parameters, and all this version of the function does is assign X to the C parameter. And you could test your program by assigning this to different parameters like G and H, which are the stack allocated ones, and make sure that you get the right value being passed back to main. Questions on the behavior of this simple IR function? So just the simplest program possible to validate whether function arguments are being passed properly and whether return values are being returned properly. All right, so let's look at how code could be generated, or one way to generate code for these functions. Remember, there are lots of equivalent assembly programs, probably technically an infinite number of them, for the same input program, the same simple I input program. But I'll show you one that I think is easy to generate, and that if you follow the instructions in CodeGen, the suggestions for implementing the compiler functions, then should make it easier to generate. Okay, so in simple IR, when you have the function declaration, which Python function in your compiler gets called? Yeah. Enter function. So the enter function is what generates code for this construct in the language. And I didn't show everything here, but the only thing so actually let me ask, what assembly gets generated when we enter the function? Yeah, the prologue. So this is the prologue here, and also the definition. So I omitted it just for space, but this is what gets generated by the enter function method. The function declaration and the prologue. All right, good. So local vars. So what does local vars do? What kind of code what does the code it generates do? Yeah.
First, it pushes space for all the local variables, and then it pushes all the allocates space for them. Right?
Yeah, that's exactly right. Yeah, it allocates space for the local variables on the stack frame. What's the stack frame? What's that? Well, it is implemented with a stack, but what is the meaning of the stack frame? I think you were, go ahead.
Yeah, it's a designated spot on the stack to hold all relevant code to a certain function call.
Yeah, all the relevant data for the function call. It includes the locals, parameters. What else does it include? Locals, parameters. What else? Return address, so we can restore the callee. Yeah, caller. And the current base pointer. Where's the current base pointer stored? Old base pointer, yeah, right. So we can restore the old base pointer of the caller. Okay, good. So this local variables, this will generate code that will allocate space on the stack in the so-called stack frame for all of our local variables. There are, how many? 9 here, and whatever the arithmetic is. I don't want to do the math, but I guess it works out. So this is generating code. And which Python function in your compiler does this code generation? enter call. So what is the syntax of a call? So this is what a call looks like in simple IR. Yeah.
For the enter call function, it's basically just calling a function, the caller function.
Right, that's what enter call does. So what is this? This is not that. What is the code that generates the assembly code to allocate space on the stack for the locals? Yeah.
I can't exactly know the name, but I know it's for the local. It's a separate function. Enter call
Yeah.
or something.
Yeah, local var. It's enter local vars. Enter local vars is the function in your compiler that does the generation. And I gave you the code for this already. Maybe that's probably why you don't remember. But all right, and the params. Yeah.
Why is it 88?
All right, let me figure it out. There's 8 of these. 9. What's 9 times 8? That's like 72. Oh yeah, I think it's an extra subtraction to get past the old base pointer, and then an extra 8 to be 16-byte aligned, which is the requirement of the ABI. What's that?
Is RC not a local variable then? Why didn't you count that one?
Oh, you're right. Yeah, 9, 10, 11 times 8. Yeah, okay, that's 88. That's the reason. Forget what I said. It was probably already stack aligned at that point. So because we had, I don't know. But yeah, you're right. It's because there's 11 locals. I just miscounted. You're right.
There's 11?
Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
No, it isn't.
Eight like things we're going to use as parameters, x, and then the 2 locals, 11. Times 8 is 11, or 88. All right, good. So params. Does anyone remember how or at least how I recommended in your compiler, we handle input parameters? Yeah.
Put them in the registers.
Well, so that's when you make the call. But the receiver of the parameters, how did I recommend we receive parameters? Yeah.
You copy all of the, first you copy the data from the registers into local variables, and then you copy and then you have the ones on the stack.
Yeah, exactly right. So how are parameters passed in the System 5 ABI for AMD 64? Yeah.
The register,
Registers and?
the stack,
Right, yeah.
going opposite direction.
Exactly, yeah. So the first six are in registers, the rest are in the stack. This only has 2 parameters, so at least the implementation I'm recommending for you in the compiler, there are lots of ways to write a compiler to do this. The easiest, I believe, is to just immediately copy all of the parameter registers into the space for their local variables. So this is RDI is the first register parameter. -8 RBP is the offset from the stack frame for the first local variable. Yeah.
I remember from the last section talking about how their copies are pushed into the stack in order, and then it's pops. Can you explain that again, please?
Yeah, we'll get to that very, very soon, actually. Yeah, we'll get to that very soon when we see the compilation of this. Yeah.
Can you remind me, how does within the function, how does it know where the variables are on the stack?
That's a good question. So how does the compiler know which offset to use for each variable? Yeah.
Create space.
So we generate code to create space. But remember, that happens at runtime when the program runs. But the compiler, even without having that space actually allocated to memory, the compiler is keeping track of some offset, like -8 for argc, -16 for argv, etc. Yeah.
Well, I meant if you have more than the 6 variables that you're passing
Oh,
to the
oh, oh,
function,
right.
for those other variables, how do you retrieve those?
Oh, we'll see that when we get to the callee. We'll see that. So hold that question for both of you, and then let me know if you don't answer that. But we'll see how we pull that information off the stack. All right. So that's how we handle parameters. Parameters just immediately copies the parameters from either the registers or the stack into their corresponding stack frame spaces for those local variables. So what I thought you were asking is how do you know the offsets, and that's the symbol table. The symbol table stores an offset. And that's given to you, and then total local vars gives that to you. Okay, so this is also code that's given to you. These are all assignments here. I'm just gonna take this whole block. This is code that I gave to you, enter assign. And we talked about this when we talked about variables. To do an assignment, we just take whatever the value on the right-hand side is, collect that into a register. So here we're moving immediate move 1 into some temporary, some scratch register here like RAX. And then to do the assignment, we're moving that data into the stack frame offset for the variable. So here A has stack frame offset -32, so we do that move. And remember, there are many ways to write this code. You could avoid having 2 moves if you want. I did it this way to make the compiler easier to write for me. Questions on assignment, enter assigned? That code's given to you. I think we went over that quite a bit as well. Okay, so let's look at the new stuff. Let's look at the more complicated stuff here. So here's the call. And so whenever we do a function call in our ABI, what are the steps that need to happen in order to make the call work with the callee? Yeah.
You pass the first 6 parameters to the register.
Okay, so we need to put the first 6 parameters into the registers according to the convention. What else? Yeah.
You have to push the remaining parameters with the existing reverse.
Right. Exactly. Yeah. Exactly. Reverse order according to our convention. You push whatever the remaining parameters are onto the stack in reverse order. That's just what the System 5 API convention is. Okay, so we pass the parameters on via registers and then via stack if needed. And then what's the next step for the call?
Return address.
Well, before we deal, so the return address. So what instruction in the assembly world handles the return address for you? Call. Yeah, the call instruction does 2 things. It pushes the return address for you, and then branches param test. And then once we've made the call and we're back executing our function, what needs to happen after that? Yeah.
Store the old base pointer, and then push the old base pointer onto the stack, point at it with the new base pointer, and then start filling all the space.
So that's what the callee has to do. The caller doesn't have to worry about that because as long as they all follow the same convention. And so what I'm getting at is just this assembly code here. This is all the caller, the function doing the calling, has to do. It sets up the parameters. In the first 6 are passed to registers. The remainder are pushed onto the stack in reverse order. It makes a call. Then it tears down the stack. And then it saves the return address. So the rest of the stack frame construction is done by the function being called. And remember, we talked about last time, as long as the 2 are following the same convention, this will work correctly. This will set up the stack frame correctly. Questions on those coarse grained steps? Pass parameters, make the call, tear down the stack as needed, and then save the return value if needed. Yeah. Yeah.
So on the subtraction above, that makes space for the stack too, right?
This subtraction?
Yeah.
This makes space for the call of main.
Oh.
Only the call of main. So each function makes space for its own local variables. Tears it down when it's done, returns to the caller, the function doing the calling. So somebody asked about the stack allocated parameters. So here you can see the first 6 parameters. So A, B, C, D, E, F, G. A, B, C, D, E, F, these are the first 6 parameters. They correspond to, they're the 1, 2, 3, 4th, 5th, 6th, etc. parameters. So these are their offsets, -32. This is parameter A, B, C, D, E, and F. So the first 6 have their data copied into the 6 registers that, by our convention, our calling convention, are used to pass parameters. Questions on that? Questions on that code? Yeah. Oh. All right. So the remaining parameters, which are G and H, so this is G and H. Oh, I'm sorry, not G and H. Confusing myself already. So you can see that we have this like descending sequence, -32, -40, etc. -72. After that, the next one is -80. So G is in offset -80. H is in offset -88. And you can see that when we do the pushes here, H is pushed first. Just because according to our convention, we push them in reverse order. So you start from the back of the list and push, 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 push. That's why negative 88 and negative 80 are in that order. Does that answer? Yeah.
So what you're saying is like the older ones are pushed first, so when you pop them, you go in order.
Yeah, pretty much. We're not going to pop them in the callee. We're going to just access them. But it's just the convention. So you have to pick one way. You have to pick an order. And I think the idea is that, it is in like order of, it's in order of distance from the base pointer, I think is why they do it. But you could pick any way you want. As long as you all follow the same convention, then it's fine. And it's based on the order that you pass the parameters in. So to make things hopefully not too confusing, but if you had swapped H and G here, you put H first and G here, these two would be swapped. Because it's not the one that's later in the stack frame, it's the one that's later in the list of parameters.
So in that one is the H, G, and F, they're pushed first.
Well, only H and G are because the first six, these first six, there's enough, there's registers for these first six. And so any after that, any others after that will have to go on the stack. And you always start at the last one. You start with the last parameter and work your way forward until the seventh parameter, pushing each one onto the stack. This sequence of offsets is just a coincidence because I use these parameters in the order that the local variables are allocated. But that will not always be the case. Depends on what order you set the parameters in. Okay, yeah.
So just to clarify, when you're moving the stack pointer up 16 at the end after the call, that's just to clear out G and E, right?
Exactly, yeah. Yeah, so this add here, this is like doing two pops of the stack allocated parameters. So notice that each function manages whatever it added onto the stack. It's like C++ programming. Whatever material it put into the stack, it's responsible for cleaning up. So you don't have to do it this way, but this convention is easier to work with because each function can make assumptions about the state of the stack when it gets called and the state of the stack when the function returns. So each function is responsible for adding and removing the same material from the stack. But yeah, that's a good question. This add corresponds to this push. That's why I had kind of silly looking code before where I added 0 to the stack pointer because I just always emit it because it's just easier to write a compiler that does that. Yeah.
Why'd you say again it's starting at 32 for the register?
It's not starting at it. It's just A has offset 32, B has offset 40.
Why is it?
That's because the order in which they're declared in local vars.
Okay.
That's where that comes from. So it doesn't have to be like that. It's just convenient to allocate these in the order that they appear in local vars. You don't have to do it that way, but it's just a convenient way to do it. And so there's no convention on how local variables are stored, as far as I understand, because it's only the local function that will work with those variables in C. Yeah. So this is what your colleague asked about, is what this 16 is reversing these two pushes. So these two pushes have the effect of subtracting 8 from the stack pointer. These are subtracting 8 from the stack pointer. So each push, at least, this push is pushing 8 bytes onto the stack and then pushing 8 bytes onto the stack. After the call, we want to restore the stack to where it was when we made the call. And this add will just reverse these pushes. Well, it's popping. It's like doing 2 pops. This is the same thing as doing pop twice. It's pop that pops 8 bytes. So, and remember, the stack pointer, whenever you push, subtract 8 bytes. When you pop, add 8 bytes. So adding 8 bytes is the same thing as popping twice when you don't care about the return value, or you don't care about the value. Does that make sense? All right, and last but not least, what does this code do? What is the meaning of the code? The move RAX, yeah.
Store the return value into X.
Right, we store the return value. So by convention, the return value is stored in RAX. So param test is expected to put its return value there. And the semantics of simple IR is to save that return value into X. This is like an assignment of whatever the return value of the call is into X. X has this offset of negative 24. So we remove whatever the return value is into 24. So hopefully you can see that these, just like when you write C, you define a contract between functions. So when you define types, you do this in C. You say, I'm going to have these number of parameters and these types. And if the function is supposed to say compute an exponent, you expect that the return value is going to correctly have an exponent. It's going to be a certain type. This is that same kind of contracts between functions, but at the binary level, at the machine code level, where by convention, all return values are in RAX. Parameters are passed via registers in the stack in this particular order. The stack is some part of the stack frame is set up by the caller, some parts by the callee. But as long as everybody satisfies these interfaces, then your code will work as expected. Questions on that? So this code, this is what call params does, and this is what enter call does, which is something that you'll need to write. I've given you a bunch of kind of helper code and ideas about how to split the list of parameters. So that's what enter call will do. All right, which piece of code does return correspond to? It's a little bit of a trick question. Yeah. The move, and only the move, at least in our compiler, in our language. This epilogue doesn't correspond to any particular piece of code. It corresponds to exiting the function node. And this corresponds to enter return. All right, questions on this code generation? Yeah. Oh, okay.
A little late, but so for the function parameters, what happens if we were to have more parameters? Because those are only store integer values, right?
Yeah, so all types in this language, simple IR, are just 64-bit integers.
Okay, and what happens if you go over the amount of, you have too many, or you put in too many parameters that are over the amount of registers that are in it? How does that work?
So this is where you use the stack. So this is why the first 6 are pushed in registers, and then there are data pushed onto the stack.
Oh,
So whatever is left, whatever parameter, 7 or more, the 7th parameter or greater, those are pushed onto the stack. So assuming you have sufficient stack space, you can have an arbitrary number of parameters on the stack. Okay, so let's take a look at in this case, what will be the callee at runtime. But the compiler doesn't have to know this. The compiler doesn't care who's calling it. Okay, so just like before, we generate the prologue with enter function. The local variables allocate space onto the stack. Params copy the parameter data from the registers and the stack into the local variable. So this is what somebody else also asked about. So just like in main, the first 6 parameters are being copied from parameter registers, RDI, RSI, etc., for the first 6. So for these first 6 registers, first 6 parameters, the code that I've recommended you use for enter params is to just generate a copy for each of the first 6 params from each of the pre-designated 6 registers into the corresponding local variable space on the stack frame. Questions on that? It's the same in main. It's the same thing we had in main. Okay, so here's how the stack parameters are handled. And there are different ways to do this. This is the way I'm recommending you do it, to move the data from the stack parameter into the local variable. So on the stack, the next parameter has an offset of 16. And, well, okay, so let me draw the stack really quickly. So when this gets called, param test is expecting that its caller, whoever it is, will push onto the stack in reverse order the last 2 parameters, h and g. So remember, we pushed h first, and then we pushed g first when we called the param test. And then what's next here? We have the return address. then the old base pointer, which is set up by the prologue. And then we had space for the local variables. That's created here. So this is A, B, C, D, E, F, G, H. So in some sense, we really have two copies of H on the stack, which is inefficient. You could write a better compiler that wouldn't do this. But compiling it this way makes it easier to write the compiler because you don't have to think about where local variables are versus parameters. You can just treat them all as local variables. So what I'm recommending you do for enter params to avoid more complicated compiler implementation is for the first 6, you copy them from the pre-designated registers. Because when we generate the call, we use those registers. This should correctly pass the first 6 parameters. When we get to the stack allocated ones, this is where our base pointer is pointing because the prologue set it up correctly. And so if we look one slot up, one slot positive, plus 8, that's our return address. So that's not one of our parameters. That was pushed after the parameters. The next slot after that is plus 16, which is our first parameter, and then plus 24, which is our next parameter, etc., if there are more parameters. So I suspect this is why parameters are pushed in reverse order, because the earlier parameters are actually a lower offset away, a smaller offset away from RVP. I suspect that's why. I don't know. But yeah, so that's why the 7th parameter, the first parameter after the register parameters, is offset 16. And so you can see here's offset 16 being copied into the local variable slot for that parameter, that local variable offset, or the local variable slot for parameter G. So here, these were, the register parameters are being stored into the local variables. You can tell they're local variables because they have negative offsets. And we do the same thing for the stack allocated ones, but we don't get them from registers. Instead, we pull them off the stack that the caller, the function that called, set up for us. So this is why we have plus 16 for G, put it into the local variable slot for G, and then plus 24 for H, that's here, and put that into the local variable slot for H. Yeah?
Do you have to do those 2 lines, or can you make it one?
I don't think you can do a store and a load in one instruction. But prove me wrong. I don't think the Intel architecture supports it. I can actually look this up because I keep getting asked this. This is the reference I use. I've linked it for you. But there's like a ton of variations of the move instructions. And I don't think, so this M means memory, R means register, and I don't think there's one where you can do memory to memory because it's like, it's 2 separate operations. It's like it's 2 separate operations on like the memory bus. So you as the compiler writer have to do that in 2 steps if you want to transfer between memory locations. So yeah, this needs to be 2 separate. If it's a move immediate, I don't think you have to do that. I think you can go immediate, do an immediate into memory if you wanted to. But I wrote it in a way that I don't do that. Yeah, so to make this even more confusing, this is Intel syntax, so the destination register is on the left, or the destination is on the left. So don't worry about that. But yeah, these have to be 2 instructions. Okay, questions on collecting the parameters and copying them into local variables. That's what this code does, and this is what the enter params function in your compiler generates. Let me move this out of the way a little bit. Don't have a good place for it. Okay, so here's our assignment. We looked at assignment already, I believe. So this is the assignment. And then we looked at return also as well. So this is the return. This move instruction. Okay, questions on how parameters are received? Questions on how functions are called and parameters are passed to them? All right, so the nice part about having these conventions and why they're in place is because you can write code separately, write and build code separately, even in other languages, and you'll be able to call functions that are written in other languages. So let me just quickly show you a couple examples of this. Okay, so here is a C program. Let me increase the size of this. Here on the left, I have a simple IR program that takes in two parameters, computes A times B. We'll go over today how arithmetic works, but computes A times B and then just returns that result. You don't really need to write a function for this. It's supported in the language, but here's a function that computes multiplies two of its parameters together and returns it. And this is a C function that calls a function called mult, gives it two parameters, and then prints the result. Questions on this code? Yeah.
It's just a random question, but how can you make your Emacs editor like just go to a spot when you're looking at it? How you can't do that?
I'm using the windowing version of it. That's why. Questions on the C code? Any questions on what's in mult.h? Mult.h just has this, a declaration. So header files generally are just used for declarations. It has no information about where the function is actually defined. If you remember when we talked about how your program gets compiled and eventually run, it's the linker that finds or makes sure that all function calls in your program have been defined somewhere. Otherwise, you get a linker error, like when you get a linker error like no main found. It's because you've linked with some other program that is trying to call main. Yeah?
What is if and then?
This is some preprocessor stuff. This is called a header guard. It prevents a header file from inadvertently being included multiple times. So it says, if this macro has not been defined yet, then enter this block, define it. And so if I call, basically if I did like this, the contents of mult.h would only be processed once because of that. It's a common trick in C.
So run errorless if you did like 10 of them?
Well, what?
There would be like no errors if you made
There'd be no errors. Yeah, there'd be no errors. This if guard will just make sure you're not declaring this multiple times. So all the header files do this. You can see standard int. You can see here that all standard header files do this. Because you might have daemon dependencies. There may be two libraries that you depend on, but they both depend on standard I/O. So they both include standard I/O. So this is just a kind of old school hack for avoiding multiple inclusion. Okay, so this calls mult, and this defines a function called mult. And so let me get my example up. I think I already have the code compiled. Okay, so here is the compiled version of the mult.ir function. This is what our compiler will generate. And so you can see the prologue, allocating space for the locals. This is the code that that copies the parameters to the local variables. This is the code that will do the multiplication. We'll go over that. We'll go over that today. And sets the return value and then the epilogue. So just like what we talked about, it uses the same ABI to take parameters in via these two parameter registers, RDI and RSI, and it sets the result of the multiplication to RAX. Questions on that? Let's look at what we just went over for handling parameters. Now, if we look at the assembly code for, do I have the assembly code here for main, for interop? So we have the C program, interop. This is the one that calls mult. I can compile it to assembly like this, and actually I didn't look at what this looks like yet. Oops, no. Oh, what am I doing? So this is what the GCC compiler generates. And so you can see that, okay, well I don't remember what the code looks like. So it's passing 7 and 3 via what are supposed to be the, RDI and RSI. So on the left here we have our mult function. On the right here we have the main that was generated by GCC. It thinks they're 16-byte. Oh, that's a mistake on my part. Oh yeah, okay. So by default these were 16-byte. I probably should have cast them to be 64-byte integers. Oh well. So it's not going to support 8-byte, 64-byte. But anyway, you can see that it's moving the first parameter, 7, into the DI register. EDI is just a 32-bit version of it. It's moving it into the EDI register, and it's moving 3 into the ESI register. So that's our second parameter. That's what will be taken as the second parameter. And then it runs call, mult. And then finally it does exactly what our compiler does. It takes the return value and stores it into its space for the local variable that it's supposed to save to, x. And then it sets up the call to printf and does printf. But you can see here that it's doing the exact same thing that our compiler does. Because that's why we can actually write code that you can call C from, and you can actually also call C programs from your code. Isn't that amazing? You don't find that amazing? That you can like generate code that the C compiler will call? You can write code? Yeah.
So I have a question about that issue of it loading into registers ESI and EDI.
Yeah.
That's a C compiler optimization that it's trying to do that would mess up the code.
No, I think it's just that when you have constant integers, they have the type int. I think that's why. So if I cast them to be, let's see if that's right. Yeah, no, I can't even cast them to be 64-bit.
Can you turn off optimizations in GCC?
Yeah, you can. There's still, it might actually, oh yeah, you're right. It might actually be an optimization, you're right, because it knows that you don't need 64 bits for 3 and 7. Well, turning off optimization didn't help. Now, if I put like some large 64-bit number in here, let's see. Let me do I'm very bad at math here. So that's 1 byte, 2 bytes, 3 bytes, 4 bytes. Let's do 5 bytes. Let's see if that'll force it to be 64-bit. Yeah, so I forced it to, I don't know why I did it this way, but I basically gave it a number that was more than 32 bits. That was 5 bytes. And it now is using RDI. So I think you're right. It is something like an optimization where it's saying, for 3, I don't need 64 bits. But anyway, minor thing. Don't worry about this. The thing to remember is that by following this convention, we can call C functions, and C functions can call us, because they're all just generating assembly code. And as long as they have the same convention for function calls, passing parameters like in the SI and DI register, or the E prefix is just whether it's 32 or 64 bits. And we pass the return value in RAX, like here, then we'll be able to link these programs together and make a single running program. Questions on that? Questions on that interoperation? Yeah.
Yeah, so, I mean, assuming it's relevant to what you're trying to get across, could you go into some more detail on the header file that you generated?
Sure, yeah. Yeah, let me show this actually working, hopefully. So here I'm compiling the C program with our output assembly program into a program called interop. And it should run and, yeah, give us 21. So it gives us the number we expect. So the C program is what defines main. And it's calling whatever this function is, getting a return value and printing it, and it's giving you 21, which is what our assembly program does. So the header file this is just a kind of a convention in C. C does not have real library management or module management. Each C file is compiled individually. And just to kind of remind you of our lecture on how a C program gets run, if we compile these two what are called compilation units individually, mult.s. So we had two programs, interop.c and mult.s, which is what our compiler generated. So we have two compilation units. They just define functions. They each just define a function. So our compiled mult.s gets compiled into an object file or assembled into an object file by our assembler, and it exports a single function called mult. So that's what this symbol table is saying to us, that we've got a single symbol in our program called mult. And in our program that calls main, it defines the main function, and because it calls mult and calls printf, this undefined here, this UND, means this binary file has no functions defined called mult or printf. It has no symbols for mult and printf. Does that make sense?
Yeah. So if you can remind me, at what stage if you just like do regular GCC mult.c, at what stage in the process does it start complaining that functions are undefined?
At the linker phase. So when we do GCC-C, that's the compilation and assembly if you do it on a GCC file. So if I were to say try to compile mult.s, what would I get? I'd get a complaint that there's no main, because the linker is also linking with the C runtime, which is what calls main. Anyway, go back and review that class. I know it was a pretty fast class because I think I had to shrink stuff for the Hurricane. But we have these two files here. The linker is what matches these two up. So if I were to try to just compile interop.c by itself, I'd get a complaint about an undefined reference to mult. And that's because I didn't provide the linker, the assembly file, or the binary file that had the definition of mult. And in my compiled version of the file, which was interop, if I look at its symbol table, it's going to have a lot of stuff in it, but it will have a definition of mult. Mult is no longer undefined. And it'll have main. It'll have both, because it took those two binary files, those two object files, and it linked them. It made sure that the definitions, it made sure that any unsatisfied definitions were now found in this linked file. I don't know if that helps. The header file is not involved in linking at all. All the header file does, so if we were to take this out and try to compile, not link, but just try to compile interop.c, we'd get a warning that mult is not defined. Now in C, if you don't define a function ahead of time, it makes the assumption that you're defining a function, I think with no parameters, that returns an integer. So it has kind of a default behavior, but it's better practice to actually declare your function so that the compiler will know what the data type of that function is. And so that's the one of the purposes that header files serves, is just providing to the compiler the data type of your function, how many parameters there are, return value, etc. So that's really all header files are. They're not actually connected to the linker directly. It's like a simulation of modules. All right, questions on this? So you can also go the other direction. We'll use this, you can use this in class to use printf or something like printf in your programs. So I'll give you an example where I define some very basic print functions. So you won't be able to call printf very easily because we don't have strings as a data type or characters. I mean, you could probably get it to work, but it would be a massive pain. So you can write a C program that has some very simple definitions like print int and read int and use printf and scanf to implement those. So any questions on these functions here? So printf just takes an integer and then calls, or print int just takes an integer and then calls printf to print it out. Read int just uses scanf to read an integer and then returns that integer. Yeah?
What's the point of the print 64?
This PRID64? This is the format string for a 64-bit integer.
Oh.
It differs on different machines, so it's good practice to use the macro to do it. And so you can actually, because if you follow this ABI correctly, you can actually call these functions from simple IR. So we can actually call readInt, and it just generates the code for a function call, and it's the linker that will make sure that code is there from our C program. The same thing for printInt. And so you can actually write some sophisticated stuff in C and then call it from your simple IR program. So let me show you quickly what that looks like. So I have a pre-compiled version of this. Well, so actually let me show you what the assembly looks like for this first. So it's just what you'd expect if you sort of grasp the function calls. So here's the call to readInt. There are no parameters to readInt, so it doesn't pass any parameters. It does the call to readInt. This is my silly add 0 to the stack pointer, which is my lazy way of writing the program. And then it just saves the return value. And that's it. That's how it calls readInt. And readInt in the C will go off and do whatever you want, whatever you've written there in the program. And similarly for printInt, this will what am I doing? This will take the parameter and put it into RDI, which is what the ABI expects, call printInt, and then save its return value. Make sense? Yeah. Yeah.
Is there anywhere in the assembly code that kind of, maybe a really bad way to put it, but is there like a version of include in that assembly file? So
No, there isn't. This is all done by the linker. So, well, there may be a pseudo op for it, but
I'm mostly meaning specifically for the read and print functions you have there.
like this.
Yeah, would that spit out an error?
No, so the compilation units are expected to have undefined functions in them. Actually, these aren't even functions. These are really just symbols. And so the object file is expected to have symbols that are undefined, and then it's up to the linker to do that. So there's no notion of a header file that I know of in the assembly world. It's really the linker file is kind of like the header file. You can actually define a linker file that specifies, I guess, like the order to do linking in. But no, instead the assembler will just create a file that has a list of, a symbol table that has all the things that are defined in it, all the things that are undefined, and the linker will line those up for you. All right, questions on this? So I'll release these examples. I don't think I released examples, but you can also do this on your own, and you can actually test your ABI against like actual C code that's generated by GCC. All right, let me get into arithmetic since I'm quite late in the class, but hopefully that's a little clear on how functions work, how the function ABI works, and how you can actually like test it with C.
Do you mean to write COP-3402 twice?
No, I didn't. Wow, that's funny. Maybe I did. I don't know. Maybe it's arithmetic. I'm adding them up. All right, so let me switch gears to how we generate arithmetic code. So this is an example of an arithmetic simple C operation. It looks just like an assignment where we have the variable you want to save the result in. We have the assignment symbol. But on the right-hand side, instead of a single variable or number, we have an operand followed by an operator followed by an operand. And remember, this is just ASCII text. This doesn't correspond intrinsically to an x86 add instruction or to a math add instruction. It's just a symbol. And so our compiler will take this IR code and it'll give it meaning, it'll give it semantics by generating assembly code that will produce the same result. And so in the Intel assembly with the AT&T syntax, this is somewhat what we're going to generate for this. We're going to generate an add instruction that will, I forgot the comma, but remember that in AT&T syntax, the destination is on the right. What makes this extra confusing is that the destination register is also the left operand of the arithmetic. So I'll show more examples of this. It makes things a little confusing. With addition, it doesn't really matter, but subtraction it does, because subtraction is not, what's the word, commutative? Is not commutative. So you have to kind of reverse in your head the order of the operands for the Intel AT&T syntax instructions. So the operands are reversed. Conveniently, these are called A and B in the two languages, although that doesn't have to be the case. Yeah?
What's the question? What if you have multiple things to add, like A plus B plus C?
Ah, that's a good question. So in simple IR, you can only do a single addition at once and in one operation. So I designed that language that way to make it much easier to map between the two. But if you had an arbitrarily long arithmetic expression, if you wanted to implement that in assembly, you'd have to break that down into individual operations.
And
Yeah.
what if you said about A plus B plus C, that would also be to A, or would that be, say, base, well, if you did it all individually, would that all the results add up to A if you saved in the memory just for A, or would that be the same?
Well, it depends on your language. So if I had a language like this where I said x equals something, so for instance, and this is the way like C works. I killed my scratch. And this is the way something like what C would look like. You'd have 1 plus 2 times 3 times y plus 4. Each of these would be decomposed into 3 operations, and the result of it would be saved in x. So you can think of this as being translated into some temporary operation. So you'd have 3 times y go first, and then you'd have a temporary variable for 1 plus t1, I think, right? And then you'd have another temporary, or just put it directly into x, for the result of 1 plus t1 plus 4. Does that make sense? So this is like, so I made this more confusing with order of operations, but 3 times y I think would go first, right? 3 times y would go first. So you do that, sorry, this should not be 7, it should be y. So let me just take away variables to make this less confusing. So you do this operation first, so you'd have to compute that and then save it in some other place. You have to save it somewhere. And then once you have that result, then you can compute this operation. And that's here.
Is it easy to Google like an example and like aggregate and assembly code?
Yeah, actually we
Thank you.
could, you mean like Google an example of what it looks like? I think we could,
do that on my own.
yeah, you could, I might be able to generate one. I could generate one and see, actually. So, so I could write a function that takes in a couple of parameters. And let's say it returns a plus 2 times b plus c. And let's compile that code. Oops. So let's compile this just to assembly. What do I call this? Operations at C. Let me make sure optimization is off, and let's see what we get. I don't see. Oh, so it's playing clever tricks with the multiplication. Let me. So we see. Oh, it's going to be annoying to interpret, but it's doing. So this is B. This is going to take me a while to interpret, but it is decomposing those into multiple adds, if that makes sense. Let me do a simpler one. Let me just add them together, because I can't read assembly very well. So we just add these three together, A plus B plus C, and this decomposes it into two add instructions. So it's saving it's putting A and B into registers and then doing the add, and that gets the result gets stored in a register, and then it's taking C, putting it in a register, and then adding the first addition to the second addition. Does that kind of make sense? Kind of. Let me go through how the actual assembly code works for assembly instructions work for add, because add only takes two arguments, but there's really three things. There's the result, and then there's two operands. So let me go over the Intel instruction set to show you how that works, and then it'll make this make more sense, I think. But you can see here we have the same thing that our compiler generates, these offsets from RBP for A, B, and C. They're 4 bytes because they're 32-bit integers, but same idea. Okay. Okay, so to convert this into assembly, we have the fact that we've got variables instead of memory addresses, so we have to convert those just like we did with parameters. We have to deal with integer constants, but we can do that with immediates. And we have to do the actual assignment. All right, so this is the syntax of operations in the language. We have a symbol followed by an operand, and in the language that I've given you, operands can either be an identifier for a variable or a constant number. These are the set of operators that we have in our language: plus, minus, star, slash, and percent. So I've given these their conventional meanings: addition, subtraction, multiplication, division, and modulo, or remainder. And then operand 2 is also an identifier or a number. So that's the language that we have for operations in simple IR. So for this example, this is a name for the destination variable that we're going to store the result in. This is one of the operands. This is a name operand, a variable operand. This is the other operand, and this is the operator. Questions on that? Questions on the syntax? And so operands can also be integers. We have these 5 operations available. Okay, so we access variables just like we did for parameters or assignment. We just take whatever the symbol table says is our offset from the base pointer and save it into a temporary register. So a lot of these operations do not work on memory. Most of the processor operations work on registers, so we copy stuff into scratch registers to do operations on them. So here we're just copying whatever variable corresponds to this offset into RAX. Questions on that? I think we saw this many times. Hopefully this is mostly review. So integer constants, we can just do immediates for that. I think we saw that a little bit, but that's a move immediate for that. So you can just use money sign and then literally copy the integer ASCII that was given by the user. Okay, so this is the subtlety. How do we save the result? Well, we do the same thing we do to save variables, but the subtle part about arithmetic is that this add instruction is equivalent to this. So RAX, yeah.
Isn't the left register used to save the result?
The destination register is, yeah, but in the AT&T syntax, the destination register is the second operand. This is what's confusing about the AT&T syntax.
Yeah, I was going through the notes, and for some reason you just left operand, and then you maybe say that it was equal to the second operand.
Maybe I made a mistake in the notes.
It's in the division part.
Okay. Oh, division is a little different. Yeah.
I didn't know which registers to use. Is that just like the
So it almost doesn't matter. So there are scratch registers you can use. RBX is not technically a scratch register, but I thought it was convenient to use it because A and B are sort of make sense as the first operand and second operand. But in the AT&T syntax, you just have to remember that for addition, this second operand is both the left operand of the addition, or of whatever the operation is, and also the destination register. So this is just how the architecture is designed. Originally, A was an accumulator register. I think that's why it was called A. I'm not sure. But the idea is that you're accumulating this into this register. So this register already has a value, and then you're taking this value, whatever it is, and adding it to the current value of this register. So it doesn't exactly correspond to our simple IR, right? Because our simple IR has 3 variables, but the addition instruction only takes 2 arguments in the Intel world, because this argument, the destination argument, is both the operand, one of the operands, and also the destination register. So it's like overwriting that value. Does that make sense? This will make the compiled example that I show hopefully also make a little more sense. So if you just remember this, that this add instruction is in our kind of intuitive math world doing this. It's taking whatever the value of RAX is, adding it to the value of RBX, the first argument, and then saving that result in RAX. That's the behavior of this machine instruction. Questions on that? And that's going to be true for addition, subtraction, multiplication. Division is even more confusing. So we'll go over division, how division works. And these are all probably due to some making like the engineering of this easier or something like that. All right, so subtraction works the same way, where the first operand, or I should say the left operand of the subtraction, is the second argument to subtraction, and it's also the destination register. So just like with addition, I didn't show the formula here, but this subtraction means this. RAX gets set to whatever RAX was first minus RBX. Okay, so the reason that this is important is that if you swap these 2 registers or you make a mistake, you might get different results. So for addition, what's the result of this add instruction? So I move 9 into RAX, 5 into RBX. What's the value that add computes? 14. What if I swap the operands? What's the value that it computes? 14. Okay, but what about subtraction? So I've just changed this to be subtraction. If I have 9 and 5 here, what's the result of this subtraction? So we have a lot of answers. What about the second one? Yeah, so you can see where this gets confusing. So okay, so remember the meaning of this subtraction. Well, this subtraction means because the second parameter is RBX, that's the destination register. So this subtraction means this. So RBX is 5 minus 9, negative 4. And the result is stored in RBX, not RAX. Questions on that? Yeah.
So in AT&T syntax, can you generally think of it as being, like if you want to just conceptualize it, like instruction, and then I guess what would it be? Object, preposition, subject, like subtract RAX from RBX, move 5 to RBX, or is that
Maybe, yeah. Maybe. I could think of it like, well, yeah, I don't know if that helps. Yeah, yeah, I think so. Yeah, I don't know. There are programming languages that I think use, the programmers use arrows. So you could think of it like this difference in syntax where the destination is on the right of something versus on the left. I don't know. I don't know if that helps. Yeah, I don't know. I don't know the best way to think of it. Yeah, move this to or add this to. Yeah, you could think of it if you want to translate it to English. That could, if that helps, if that's helpful. Yeah.
Why'd you send the slide addition?
Because I made a mistake. Sorry. So this subtraction, what's the result of this subtraction? 4. So RAX is 9. That's going to be the left operand minus RBX, which is 5. That's 4. And where's the result going to be stored? RAX. So the second argument is the destination register in the Intel world. All right, questions on this? So you just have to get used to it in the AT&T syntax. All right, multiplication works the same way. And it's commutative, so it wouldn't make a difference on the value. But remember, the write register is the destination register, and so you may not get the result you expect if you make a mistake and swap these arguments. All right, so okay, so I think I have a full example here. Yeah. Excuse me. So here's a full example of having two local variables, a and b. We assign them to 9 and 5, like we did in our example. And then we add them together. Let's look at what the translation of this to assembly would look like. So this is what our offset table will look like, our symbol table will look like, because we just allocate each local variable in order in our local variables. So we get -8 for x, -16 for a, -24 for b. Questions on this? I think we've seen this a lot, I think. So first, there's 3 steps here. One is we take the data that we're trying to operate on, put them into registers, so that's the a and b, the values of a and b, perform the actual arithmetic, and then store the resulting data that we get back into a variable, the variable that was told to us by the developer. Questions on these 3 steps? Okay, so let's see what these 3 steps look like just for x equals a plus b. So this is the code that we've seen many, many times, I think, by now, to load the values of variables into a register. So this is loading from memory the offset -16 from the base pointer into RAX. So that's the value of A. And then load the value of B into the register RBX. Questions on that? We've seen that, I think, several times. And here's the addition. So remember, excuse me, the destination operand is on the right or the second operand on the add instruction on the arithmetic operations. So here's how we compute the results. And it doesn't really matter that we've changed the value of RAX because the kind of official value of A is here in memory. We haven't touched that. We've just taken this temporary register and generated instructions that will update it to be the result of this addition. And then we save the result that we have, RAX, into whatever variable that our assignment asks for, which in this case was x. Questions on this code? Okay, so integer constants are very, very similar, except instead of loading from a variable, we'll just load from an immediate register. That shouldn't be negative. We'll load from we'll do an immediate load, and then everything else is the same. Just do the addition and store the result in x. Yeah.
The 7 should be positive.
Yeah, it's not supposed to be negative. Apologies for this. It should not be that. Yeah.
If it was, if you did want to make this, would it be $7?
Yes, it would be $-7. That's right. Yeah.
If one has the register the memory address be a negative value, like say one turn, if they're doing A minus B, one piece needs to be negative, would you percent sign minus or how would you do that?
No, you wouldn't have to. The register itself would hold a negative value. Be like 2's complement negative values or something like that. There's an encoding in the machine level for negative numbers. They are encoded with what you might think of as positive. I mean, they're just encoded with binary digits. So like half the digits are allocated to subtraction. Machine handles all this for you. You don't have to worry about that. So yeah, this shouldn't be here. Okay, so before we get into division, let me show that example. So here was the C program where we have, this is C now, not simple IR, where we have 2 additions. And A, B, and C are in -4, -8, -12 offsets. So you can see here that, it's a different allocation of registers than in our language, but this is storing or loading A into EDX, into the DX register. This is loading B into the EAX register. This is just computing EDX equals EDX plus EAX, right? Because the EDX is the destination register. This is loading C into EAX. And then this is computing EAX equals EAX plus EDX. So if you work all that out, that looks like A plus B plus C, right? I think. So this is A plus B, and the result of A plus, so this, this is the result of A plus B saved into EDX. And this is the result of C plus A plus B, or C plus EDX saved into EDX. So EDX was A plus B, so this is computing C plus A plus B and saving the result in EAX. So it'll be the return value. Does that make sense? Did the compile make more sense? So yeah, I think you have to know the Intel instruction set for it to make sense. But yeah, you can see what if we did like a full compiler that could do math expressions, we would have to decompose the expression into all of its individual instructions and work out all the intermediate values to do that. But in our language, simple IR, there's only one instruction per operation, making this far, far simpler to deal with. If you want to see how to do expressions, take my compiler construction class every spring, and we'll go over actually like parsing and doing that code generation. All right, questions so far? All right, let me go over division, because division is very, very specific on the Intel instruction set. So unlike add and subtract, you can see here the division instruction only takes a single register. And that's because division only works with certain registers. I assume they do this just to save money, so they don't have, I think the adders, there's lots of adders probably in the machine or something, I don't know the exact reason, but you have to use very specific registers in order to do division on the Intel instruction set. So specifically, RAX always holds the numerator, the first operand of division, and then you do the division giving it the denominator, giving it the register that you want to do division with. Does that make sense? So EAX or RAX is always the first operand of the division. Yeah. Yeah, that's a very, very good question. So division operates on two registers. You can do I think it's 128 bits divided by a 64-bit number. And so in order to get a 128-bit number, you would take two registers. Now, if you don't want to use two registers, you can do CDQ to just fill up RDX with whatever bits it needs. So this is because of the sign bit. I think, did they teach you about sign bits and 2's complement in CDA? Yeah, so this has to do with that, where RDX needs to have the sign bit as well for 2's complement representation. And so CDQ, if you only have the value for your numerator for your division in RAX, CDQ will ensure that RDX has the right data for that division. So you don't have to worry too much about this. Just know that you put the left operand of the division in RAX, you call CDQ, and then I divide with the right operand of the division. So again, there's nothing really to learn here. This is just the instruction set we're given. This is how it works in this instruction set. And the results are always in two very specific registers. The quotient, that is the result of the division, integer division, is always in RAX, and the remainder is in RDX. So the same operation is used for both division and modulo. Let me see if there's... So I actually have assembly code here. There's still 2 minutes left. I'll just quickly go through this. So questions so far on this, just the instruction set design? Okay. So yeah, I already went through this. So here's an example. Same as before, except we do A divided by B. Here's what the assembly code looks like. Set up the operands. Perform the division. So because we stored RAX in here, we perform the division with CDQ and then IDiv the right operand. And then we store the result, which will always be in RAX, into X. So for modulo, All the only difference is which register you take the result from. RAX holds the quotient, the result of the division. RDX holds the remainder. And that's it. So this is all documented here. I'll give you the Intel x86 documentation. I'll give you tips in the CodeGen 3 project. But yeah, still a minute to spare. So questions on this? All right, so that's arithmetic in in Intel, and then CodeGen 3 will be your project where you implement this. All right, everyone, have a good one.